Transformers have become extremely powerful and extremely popular. But as these models get larger and larger, the real bottleneck is no longer intelligence, it's computation. So the key question becomes, how do we reduce compute while preserving performance? Broadly, there are two paths. The first and very popular approach is post-training quantization or PTQ. Here we train the model normally in high precision, say floating point 16 or floating point 32, and only after training do we quantize the weights to lower precision. This does reduce memory and inference cost, but there's a catch. The more aggressively we quantize, the more distortion we introduce, and that distortion shows up as a drop in accuracy. Even worse, once the model is quantized, fine-tuning becomes extremely difficult or impossible because the training dynamics were never exposed to low precision noise. So PTQ works, but it's fragile. The second approach is far more interesting. Instead of quantizing after training, we change the training process itself. This is called Quantization-Aware Training or QAT. Here the model learns from the beginning under reduced precision constraints. So it adapts, compensates, and it learns representations that are naturally robust to quantization. As a result, QAT almost always achieves higher accuracy than post-training quantization. And it also allows continued training and fine-tuning. And this is where BitNet comes in. BitNet pushes quantization to the extreme. During training, weights are effectively reduced to 1 bit values, typically +1 or -1. The input activations still might be floating point 16 and weights may be stored in floating point 8, but during computation the weights are binarized. This is done through a simple absolute quantization process. We center the weight by subtracting the mean, we scale using maximum absolute value, and we quantize to binary representations. After computation, the output is dequantized using learn, scale and shift parameters given by gamma and beta to map results back into floating point space. So training happens in a very different numerical world, but inference still operates in a usable continuous space. So here's the key insight. Most of the computation in transformers happen inside linear layers, QKV projections in attention and feed forward networks. And BitNet or BitLinear replaces all these linear layers with quantized versions. And once weights are only +1 and -1, something remarkable happens. Matrix multiplication turns into simple addition and subtraction. No expensive multipliers, just adds and subtracts. And from a hardware perspective, multiplication is far more costly than addition. This means lower energy, fast execution, better hardware utilization, and massive scalability benefits.